The Philips Research Center near Eindhoven in the Netherlands is one of our centers working on a wide range of scientific disciplines. Charge-coupled devices, known as CCDs, were first developed by Philips over 20 years ago, and the first image sensor was proposed and patented in 1966. We have come a long way since those first steps, as we will show you in the next few minutes, but the basis principle remains the same: converting light into electrical signals using photon-sensitive CCD devices. Philips imaging technology is a part of the Philips Research Center near Eindhoven and is the development and production center for Philips CCD sensors. As well as they are used in broadcast color cameras, CCDs can be used in medical, industrial, and security applications. The design and production of a CCD is a very high-tech process. Computers used throughout this process are first used to design the circuit structure of the CCD and the connections that must be made to it to enable outputs and inputs from the outside world. From this design, masks are made, which will be used in the etching process. Clean conditions are the key to successful sensor production, and that goes for the people who work in this area. Special clothing must be worn over everyday clothing to prevent any contamination. Only when the operatives are in their protective clothing, they can enter the clean room where sensor production takes place. There are two areas within the sensor production plant which must have very clean air conditions. This is the service area where access can be gained to the rear part of the sensor processing equipment to facilitate maintenance. It is not necessary for the air here to be filtered to the same high level of cleanliness as is required for the actual production area. In the area where sensors are manufactured, the air must be filtered to a much higher degree, and here filtration reduces contamination to 10 parts per cubic foot. The first step in the production process is to clean the wafers of silicon. It is important that no contamination is present on the wafer surface, which would alter the design of the sensor, making it useless. Most processes are automated to limit handling by the operatives, thus reducing the chance of contamination or damage to the wafer. Here, chemical cleaning is used, and after cleaning, the wafers are rotated and dried. At every stage of production, quality controls are implemented to ensure that each process is correct. Here the surface of the wafer is scanned to ensure that the cleaning process has worked correctly. After surface scanning, the results of cleaning are recorded for statistical control. This stage, where the oxide layer is grown, requires an oven temperature of 1000 degrees Celsius. Of course, the plastic cassette used in the cleaning process would melt at such a temperature, and so the wafer must now be relocated in a quartz cassette. The high oven temperature and the introduction of oxygen causes an isolated oxide layer to be grown on the silicon wafer. The thickness of this layer is checked and controlled to a high degree of accuracy. Etching of the wafer requires a mask to enable those parts which will be the final sensor to be formed. We use a light-sensitive layer on the wafer which, when exposed to white light through a mask, will expose this layer just as in a film camera. The general lighting in the production area is yellow, similar to darkroom conditions used in developing black and white film. This prevents accidental exposure of the light-sensitive layer on the wafer. Earlier, you saw the masks being developed in the computer-aided design stage. The wafer with its light-sensitive layer and mask can now be exposed. In this process, we use a stepper, which moves the wafer with accurate precision, exposing it to white light after each movement. Far greater accuracy is possible using this technique than would be possible if the whole wafer were to be exposed at one time. Just as in photography, the exposed light-sensitive layer on the wafer must be developed. As at all stages, the wafer is once again inspected, this time using an optical microscope. We must be sure that during exposure, accurate focus was obtained, that the wafer has been correctly aligned, exposed, and that it is still clean. During this process, the wafer is handled automatically. Once the control procedures have established that the exposed mask layer is correct, in every detail, the etching process can be carried out. Using plasma, the exposed parts of the wafer silicon layer can now be etched away, forming the initial construction of what will be an image sensor. To look at the minute detail of the etched wafer, it is necessary to use an electron microscope with a magnification of between 10 and 20,000 times, far beyond the possibilities of optical microscopes. This is a further check of the quality of the layer. Implantation or doping of the etched silicon is required to form the elements of the sensor. This is a controlled and deliberate contamination of the silicon by the introduction of ions. This whole process may be repeated a number of times before the final sensor construction is completed. At every stage, the correctness and quality of each process step is recorded and stored in a computer database for statistical purposes. This enables maximum control of the whole production process to be realized. The individual elements of the sensor must be connected together as required by the sensor circuit design. This is done by a metallization process, bonding these elements together. Once the metallization process is completed, it is carefully checked to ensure that all correct connections are made and that no short circuits or faults are present. When these checks are completed and we are sure that the sensor is perfect at this stage, then the final assembly stage can be started. The wafer contains a number of sensors, which must be separated into individual sensors. The wafer is now cut using a diamond cutting tool, and once more carefully washed to remove any particles left behind in the cutting process. Examination of the sensors using a microscope again controls quality and cleanliness, which are of prime importance when considering the minute scale of a CCD image sensor. The individual image sensors are now bonded to the housing, which will hold the silicon firmly in place. A type of superglue is used in this process, which is placed on the holder, the sensor then being placed in position. This whole process is once more fully automated, minimizing handling by operatives. Finally, the connections to the outside world are made. In this automatic machine, bonding wires are connected to the pins of the sensor housing, holding it. The sensor is now complete and ready for use. Philips Imaging Technology designs, develops, and manufactures a comprehensive range of CCD sensors. This is the highest technology available in the world today, advancing the frontiers of scientific achievement.